Hello everyone. In this video we're going to learn about a very important notion called continuity. So informally the idea you should have is a function is continuous if we can trace the function without lifting our pencil. So the idea is, let's look at a little example. We have our graph here. This is the x-axis, y-axis. I'm going to draw the function in green. So if I have something like this is my function. Notice I was able to draw it without lifting the pencil or without lifting your finger. This is the idea or the informal definition of continuity. This is what you should be thinking of. A non-example, so this function here is continuous. A non-example would be something like this. We have our function here, there's a hole, and then it continues here. So let's call this function g of x. So notice there's a hole over here. So if I trace my function, well, in order to continue, I have to lift my pencil, come here, and then continue on this segment. So in this case here, the function is not continuous, okay? This is one example of a function which is not continuous, and we're gonna look at a more formal definition. Okay, so now that we have an idea of what continuity is, let's take a look at a formal definition. So a function f is continuous at a number. We also have continuity on an interval, but right now we're dealing with continuity at specifically a value, in this case a, if the limit as x approaches a of f of x is equal to f of a. This is our definition. So the way I want you to think of it is that it breaks up into 3 steps. We can remember it this way, but really I think it's instructive to look at all 3 cases. And the first one is, think of it as the function has to be defined. So that's our first thing that we need. F of a needs to be defined. Okay, so if I graph this is my y-axis, this is my x-axis, well, f of a needs to be defined, meaning that has to be a point here. Okay, let's put the block point here. This is at a, and this is our f of a. That's our a value, that's the y value. So that's the first thing that we need. We need our point to be defined. Step 2. We need the limit to exist. So we need limit to exist. Okay, and we saw in a previous video, in order for a limit to exist, we need the left-sided limit and the right-sided limit to be equal, to match. So in brackets, let's put a limit from the left as x approaches a from the left of this function, let's call it f, is equal to the limit as x approaches a from the right side of f of x. So this is the idea that we're thinking. We know this is our definition for a limit to exist. Okay. But there's an issue, because we could have the point defined over here, and we could have the limit existing, such as, I don't know, over here. From the left side and the right side, the limit meets. Okay, so left side, right side, the limit exists, but the point is defined over here. This would be an example of a function which is not continuous. So what's the third step that we need? The last step in order to make this continuous is to ensure that the function is defined where the limit exists. Okay, so in order for this to be continuous, and this in a sense makes sense because of our intuition that in order for a function to be continuous, I should be able to trace it without lifting my pencil, and here I would have to lift my pencil to come get this dot and then continue back up here. Okay, so the third point is that the limit has to exist where the point is defined. The point is defined at f of a, so the limit is equal to f of a. And these are the 3 conditions required in order to have continuity. So this wouldn't be up here. The function would look something like this. Okay. So at this point here, the function is continuous because the left side of the limit, the right side of the limit, they meet. That's condition 2. The point is defined, it's there. And we combine everything like a chain. The limit exists where the point's defined. Okay. So this is an example of a function which is continuous. And this is our definition that we have to keep in mind. Okay. Let's take a look at a couple more examples, and we'll look at functions which are not continuous. So here we're going to look at the 3 types of discontinuity. So on the board I left the conditions for continuity, so these are the 3 conditions that we just saw. The first type of discontinuity, so now the function is not continuous, meaning that we have to lift our pencil in order to trace out the function. The first type that we have is something called removable discontinuity. Okay, so if I were to draw this, a removable discontinuity could look something like this, where you have, let's say, a straight line, a hole, and then the function is defined up here, and then it continues back over here. So notice that at this value a, let's call this a, there's a hole which I have to lift my pencil, come touch this point up here, lift my pencil again, come touch the function here, and then continue. This would be an example of a removable discontinuity. And the reason why I kept this is I want you to see which condition fails for removable discontinuity. Okay, so f of a needs to be defined. Condition 1 is fine because the point is defined, it's defined up here. Needs a limit to exist. Again, the limit here exists because the left side of the limit, as we approach a from the left side and as we approach a from the right side, it's approaching the same value, essentially where the hole is. So whatever that value is, let's call this L. From the left and from the right, the function is approaching the value L. So the limit exists. Condition 2 is satisfied. But notice that condition 3 failed because the limit does not equal where the point is defined. So the point is defined up here, the function converges towards L, so as x approaches a, so condition 3 is not satisfied for continuity. So this would be an example of removable discontinuity. Another thing for removable discontinuity, the point actually does not need to be defined. You could have just a hole. So this would also be considered removable. Okay. So this one here fails essentially 3, and at times it could fail 1. So conditions 3, 1, and 3 failed. So this is an example of removable discontinuity. Okay, so that's the first one we have to know. Let me box this. The next one that we have, type 2, let's do the jump discontinuity. Oops, jump. An example of a jump discontinuity would be something that looks like this. We have our function y, x, and we have a function which is flat at, let's say, 1. Let's put 2. Comes over here, we have a solid dot, and then let's say at 1 it continues over here. Okay, so as you can see, the function is flat at 2, and then at this point it jumps down here and then it continues over here. So why is this not discontinuous? So based off our intuition, again, we had to lift our pencil to trace out this function. I had to come here, I have to lift my pencil and then continue down here. So that's definitely discontinuous. But which of our conditions fail? So let's call this point A on the x-axis. So f of a needs to be defined. That's fine because at A our point is defined. It's the solid dot over here. The limit needs to exist. Is that the case over here? Well, no, because the left-sided limit, so as we approach A from the left side, so a bit smaller than A, the function that we're hitting is up here, it's at 2. Yet, when we're taking the right-sided limit, A slightly bigger than A, we're coming over here at 1. So the left-sided limit is 2, the right-sided limit is 1. So since the left-sided limit and the right-sided limit do not equal each other, the limit does not exist. So this one here fails condition 2. Okay. And since the limit doesn't exist, obviously condition 3 is failed as well because there's no limit. There's no limit as x approaches a of f of x. So let's say condition 2 fails for jump discontinuities. Okay. So that's jump, we have removable, we have jump, and lastly we have infinite discontinuities. Infinite discontinuities. So for infinite discontinuity, you have something that looks like, let's draw our function. You have a function here that shoots up. We have our asymptote, let's just say here. And then let's say the function continues down. Okay, so our function's in green, f of x, and the value a is the asymptote. Okay. So this is an infinite discontinuity because here this takes off to infinity. So at some point I have to lift my pencil, then continue on this segment here in order to continue. So this is an example of a discontinuity. Let's look at our conditions. Which of the conditions fails over here? Well, f of a needs to be defined. So right away condition 1 fails because at a we have an asymptote. So there's actually no point where the function is defined, right? There's no solid dot here. So condition 1 fails. So 1 fails. Let's check 2. Does the limit exist? Well, from the left of a and from the right of a, they're both going to infinity. So the left side limit and the right side limit here are equal. They both tend to infinity, so that's fine. And is infinity equal to where the point's defined? Well, condition 3 also fails because f of a is not defined. So 1 and 3 essentially fail. Okay. We could put 3 as well, but obviously if 1's not defined, that's a consequence of that. So these are the 3 types of discontinuities that we have to know. Okay, so let's take a look at a couple of examples. Okay, so in this example here, they ask us to find the discontinuities. But instead of giving us a graph, now they give us a function. So we have f of x equals x plus 3 divided by x squared minus 1. So how do we find the points of discontinuity? Okay, and also, when they're asking us to find where a function, the interval for which a function is continuous, it's customary to first find where it's discontinuous, and then everywhere else it's going to be continuous. We're going to see why this is the case later. But finding the points of discontinuity given a function requires us to keep in mind 3 different notions. So there's more functions that have different types of discontinuity, but the main 3 that we use are 1, if you have a rational function, so let's call it p of x. We have the numerator n of x and the denominator is d of x. Whenever you're dividing, what can't we divide by? This is the idea. So we're not talking about limits anymore, we're talking about actual functions. What can't we divide by? So I hope you're able to answer that and see that the denominator cannot be 0. We can't divide by 0. We're not talking about limits, we're talking about the actual function. So division by 0 here doesn't work. So we know this isn't going to work. The function's not defined when you're dividing by 0. So this is one of our main cases that we're looking for. So without giving an actual graph, given just the function, if it's a rational function, this is the first thing that comes to mind. The other functions that we have to worry about are square root functions, or really it's so let's call this polynomial. Let's call it rational. So 1 is rational functions we should be worried about. We have to worry about square root functions. What are the issues with square root functions? Well, I shouldn't say just square root, it's really any even powered root. So let's put n. Let's say you have a function that looks like this. Let me put 2n. So it's any even powered root. What's the issue with square roots? Well, you can't have a square root of a negative number. So here, x has to be greater than 0. This is something we have to worry about. Actually, it could be greater or equal to 0, because square root of 0 is still 0, so that's fine. The third one is log functions. Log, or natural logs. If we have f of x equals log, let's take base a of x, well, inside of a logarithm, you could try this on your calculator, you can't have negatives or 0. So x in this case has to be strictly greater than 0. Okay. There's other issues, like tangent functions, we have asymptotes and stuff, but these are the main 3 that we're going to be looking at for now. So right now, in this example here, we're worried about dividing by 0. We have to find the values of x for which we are dividing by 0. So let's go ahead and do that. So just keep this in mind. But to solve the question over here, we're going to let the denominator, which is x squared minus 1, equal 0. If you want, you could put it cannot equal 0. That's probably a bit more accurate. And now we have to solve this. So a lot of you guys are thinking, bring the negative 1 over, solve for x. This is fine. If you bring the minus 1 over, you have x squared cannot be equal to 1. And then we square root both sides. Square root, x equals 1. Or x cannot equal 1. If this is the answer that you got working on this by yourself, that's incorrect. Or I should say it's half correct. Because if you're going to solve it this way, it's fine. Just you have to remember that whenever you're taking the square root of a value, there's two answers. There's not one. Okay, so it's not one the answer. The answer is x cannot be, this is important to remember, it's plus minus 1. Okay, so there's two values. So this is why I avoid solving it this way. The way I go about it is I always factor first. I strongly suggest to practice your factoring techniques because it comes out often. So x squared minus 1, what I see right away is instead of doing it this way, let's call this method 2. This is method 1. I'm using difference of squares here. So x squared minus 1, you could square root both terms. It's a binomial and it's separated by a subtraction sign. These are all the requirements for difference of squares. So the square root of x squared is x. So essentially what we do is open two brackets. The square root of x squared is x. The square root of 1 is 1 plus minus 1. And now we're multiplying two numbers and it's equal to 0. The only way for that to be possible, zero product law, is if either the first term or the second term is 0. That's the only way you can multiply two numbers and get 0. One of the two terms has to be a 0. So either the x plus 1 is 0, or in our case cannot be equal to 0, or the second case is x minus 1 cannot be equal to 0. Moving over the terms, this way is better because we won't forget the fact that there's two answers when we square out our answers. We're actually given two terms to solve for. So this is why I would go ahead and do it this way. So our two values for which we have a discontinuity in this function is at -1 and +1. Okay, and those are our two discontinuities. Let's keep looking at examples. Okay, so in this example here, again, we're still asked to find the discontinuities. Where do we have a discontinuity in this case? Well, we're given the function f of x is equal to, and we have a piecewise function. So this is saying x, if x is greater than 0, the function is equal to 1 when x is equal to 0, and it's equal to -x for all x values smaller than 0. So it's always a good idea to sketch these things. And typically, when you're given a piecewise function, the things we have to be worried about are jump discontinuities. Those are the ones that usually appear. But let's go ahead and draw this just to see what type of discontinuity we're working with. This is our y-axis, this is the x-axis. This x value is 0, so it follows the value of x if x is greater than 0. So x is essentially just a straight line, so it's going to look something like this. When x is equal to 0, it's at 1. So there's a solid dot here. This would be an open dot. And it's equal to -x if x is less than 0. So -x, the slope is coming down. So it's going to look something like this. Okay. So based off the drawing now, it's easy to see where the discontinuity occurs and what type of discontinuity we're dealing with here. So in this case, it's not actually a jump, it's a removable discontinuity. Okay. So what we could do here, if you didn't want to sketch this, is you could also just take the limit as x approaches 0 from the left and the right. That's another way of verifying without sketching. So you could take the limit, because remember our condition, our second condition, the limit has to exist. So does the limit exist at 0? You're looking at these values here. This limit exists at 0. So we're going to check 0 from the left side of the function and see if it's equal to the limit of this function from the right side. Okay. So now what you have to do is ask yourself, the limit of as x approaches 0 from the left side of this function here, which of the three are we using? We're approaching 0 from the left side, so that's a value that's slightly smaller than 0. Which one are we using? So since we're going slightly smaller than 0, the function that we have to use is the one where x is defined for all values of x less than 0, strictly less than 0. Okay, because even though it's to the left, it's very close to 0, it's still smaller. So we're using -x. So you're taking the limit as x approaches 0 from the left of -x, and you want to see if that's equal to the limit as x approaches 0 from the right side. So which function are we using if we're taking x approaching from the right side, or a value that's slightly bigger than 0? We're using x if x is strictly greater than 0. So we have to use x, because it's defined for all x values which are bigger than 0. Okay, so we're using this one over here. Now we substitute the limit, replace 0 in here, so we get -0 is equal to 0. Is that true? In this case here we have 0 as well, because the limit as x approaches 0 from the positive side is still 0. So we get 0 equals 0. So the limit exists. Condition 2 is satisfied. So this is not a jump discontinuity, because the left side limit and the right side limit meet. Okay, so that didn't fail. That's okay. But what you can do is check the third condition. Does the limit exist where the function is defined? So at 0, let's say at f of 0, what's happening here? Well, the function at 0, when x is 0, the y value is 1. The limit is equal to 0, so you can see the function as we approach it from the left and from the right. The y value that we're approaching is 0 on the y-axis, 0, yet the function is defined at 1 at this point. So the limit is not equal where the function is defined, so this is not continuous, clearly. Okay, I think the drawing helps. I strongly encourage you guys to always sketch if possible, but you could get it without sketching as well. Okay, so we have a discontinuity at x equals 0. Okay, so you state the x values where the discontinuity occurs, and we could be more specific. We could actually say it's a removable discontinuity, which we'll see later. We'll see how to differentiate between each type. Okay, let's keep practicing. In this example here, we're asked again to find the discontinuities, and the function that we have is one some more, it's a piecewise function. So it's saying use x plus 2, use the function x plus 2 if x is smaller than 1, the function is equal to 3 if x is equal to 1, and the function is equal to x squared if x is greater than 1. So again, I would always suggest to sketch this, so let's give this a quick sketch. This is our x, y. So when x is equal to 1, the function is equal to 3. So when x is 1, the y value is 3. Let's put it up here. So it's defined at this point. When x is smaller than 1, it's x plus 2. So essentially the y-intercept is 2 and it has a positive slope of 1. So the line's going up, it's a straight line. Let's say this is 2. It's going to look something that looks like this. So from left to right it's increasing, so the slope is positive and it crosses the y-intercept at 2. Satisfies our conditions. Equal to 1, and then x squared if x is greater than 1. So if we plug in 1, we get 1 squared, which is just 1, so it's going to look something over here. And it's going to shoot up like this, like a quadratic. Okay. So based off the picture, we could see that the function is discontinuous. And the type of discontinuity that we're dealing with here is a jump, because it comes up here, it's continuous, continuous. This is fine, and then it jumps down here. So we have a jump discontinuity. We have a jump discontinuity. At x equals 3. Oh, sorry, at x equals 1. Okay. Again, if you didn't want to sketch this, you could have done this without the visual by evaluating the limit. So typically when you have a piecewise function, you check the left side of the limit and the right side of the limit at these values here. So let's go ahead and do that. We'll take the limit as x approaches 1 from the left side of this function and see if it's equal to the limit as x approaches 1 from the right side of the same function. Since we're taking the function from the left, so a value that's smaller than 1, we're using this function here on top. So limit as x approaches 1 of x plus 2, is that equal to limit as x approaches 1 from the positive side now? And this occurs, since it's 1 from the positive side, slightly bigger than 1, we're using the function x squared. So we evaluate the limit. This is one-sided limit. We just substitute the values in. If we replace our x with 1, 1 plus 2 is 3. Is 3 equal to, on this side, we replace the 1 in here. 1 squared is 1. 3 is not equal to 1. Therefore, we have a jump discontinuity. Jump discontinuity. In this case, it's not really asking for jump. We know we have a discontinuity because it failed condition 2. The limit has to exist. Since the left-sided limit and the right-sided limit don't exist, we could claim that the function is not continuous or discontinuous at x equals 1. Okay. Okay, so we spoke about continuity at a given point, but now we have continuity on an interval, so let's just define that quickly. A function is continuous on an interval I if it's continuous for every number on the interval. So it's essentially the same definition but applied to every number on the given interval. And then now we have continuity on an entire interval. So that's the definition. I have a couple of theorems here I just want to state. I won't prove them. This is just to keep in mind. So theorem 1, if the functions f and g are continuous at a given point and c is a constant, then the addition of two continuous functions, so if you add two continuous functions, it remains continuous. If you subtract two continuous functions, it remains continuous. If you multiply a continuous function by some constant, it stays continuous. If you multiply two continuous functions, again, it remains continuous. If you divide two continuous functions, provided that the function on the bottom is not equal to 0, again, we have continuity. And lastly, if we have the composition of two continuous functions, they remain continuous. So continuous functions are very well behaved, and doing these operations on them, we keep our continuity. Okay. Another thing to keep in mind, I'm not going to prove this, but this is just a theorem. Polynomials are continuous on their entire domain. So from negative infinity to positive infinity, polynomials on its own are always continuous. So this is like x cubed, x squared, the addition of x squared, so like 3x squared minus 4x plus 6, that's continuous. So those are examples of polynomials. Those guys are always continuous. And rational functions are continuous on their domain. So as we saw, the key here, it's not on the entire domain. It's not from negative infinity to infinity. It's for all the values except where the discontinuities occur. So in the previous example, we saw it was discontinuous, I believe, was x equals -1 and at +1. So if it's discontinuous at -1 and +1, then it's continuous everywhere else. So that's what this is saying.